All right, so let's have a look at problem 9.52, in which from week 9, which we have a diesel cycle with a compression ratio of 16 and a cutoff ratio of 2. Right, so just remind you guys, compression ratio, that's going to be the ratio of the maximum volume of my cycle over the minimum one, and the cutoff ratio is the ratio between the state after my combustion process and before my combustion process, right? So right after the heat addition process. Air is at 27 C and 95 kilopascals at the beginning of the compression process, so that's going to be our P1 and T1. And we need to account for the variation in specific heat, right? So don't forget that whenever we see this, we can't use our CP, CV's approximations. We actually have to use a table and get the data out of the table. Okay, we are to determine the temperature after the heat addition process, so that's going to be the temperature at the third state. We'll see in just a second. And the thermal efficiency and the mean effective pressure. Okay. So, you guys recall the diesel cycle. I have a PV diagram here illustrating it again. We start down here on state 1. This is where the compression process happens, isentropic compression. Okay, we have data for state 1 already. Then we have our heat addition process, yeah, and we know that the volume of this guy over the volume of this guy is 2, which is our cutoff ratio. Then we have our expansion, isentropic expansion happening from 3 to 4, and we finish off with the heat rejection process from 4 to 1 on an isovolumetric change. Yeah, so from here to here, no volume changes. Now we have all the information that we need from this state here. We have the ratio between the volumes of the maximum and the minimum states, and the maximum volume, if you guys notice, the maximum volume is over here, 4 and 1, and our minimum volume is over here, 2. Yeah. So let me rewrite this because I put it wrong. The maximum volume we can have is 1 or 4 in this one, and then the minimum one is 2. So the ratio between these two volumes is 16, and the cutoff ratio that we also have, it's an order, is 2, which in this case is 3 over 2, right? So volume of 3 over the volume of 2, which is our heat addition process. Okay, so the first thing we're asked is to find temperature 3, right? The temperature right after the heat addition process. So we're after T3, okay? How are we going to do that? Well, we have all the information from 1, so we're going to use that information to find information for 2. We're going to use that information to find for 3, and then since we're going to have to find other things afterwards, we're going to use this to go to 4, right? That's usually how we solve these cycles. So let's have a look. So I went down into table A17, and I looked at temperature 300 Kelvin, that's our 27 C at the initial state, and I grabbed my VR1, and I grabbed my internal energy 1. Okay, I'm going to use VR1 to calculate VR2, because we know that there's a proportion, since it's an isentropic process, we can now there's a proportion between VR1 and the V1 or V2. So I can calculate my VR2 by saying VR2 equals VR1 times the ratio between the volumes, and we know that ratio because we have the compression ratio, right? So it's simply going to be my 621.2 divided by my 16, right? Which is the ratio between them. Because this guy over here is going to be 1 over 16, right? Cool. So with that, I can grab my, let's just go this way. I can grab my VR2, which is 38.82. And with this information, I can go to the table again, A17, and I can find 38.82, and you'll notice that I already grabbed the this is my VR right here. Okay, I already grabbed the just a part of the table 17. So we have our temperature here on the corner, and we have our VR over here. So I'm going to have to interpolate this for the 38.82 that I just found. And with that interpolation, I can find heaps of information, right? All from this table. So what I'm going to do is I'm going to grab my temperature, T2, from this interpolation. I'm also going to grab my internal energy 2, and I'm going to grab my enthalpy 2. Right? Not sure what I will need at this moment, but I'll grab all of these just because since I'm here, right, and I did the interpolation, that's the easy part. So I got 162.3 Kelvin over here for my T2. For my U2, I got 643.34. And for my enthalpy, I got 890.9. Always keep in mind these guys are kilojoules per kilogram, right? Kilojoules per kilogram. All right, so now that I have my T2, I can take advantage of the fact that this is an ideal gas, right? And I can go ahead and do my P2 V2 over my T2 equals my P3 V3 over my T3. Now, the pressures are the same because we know diesel cycle has a isobaric heat addition process. We can look at the graph if we forget. So these guys go away, and then we're left with we're looking for T3, right? That's our part A of the question. So we see that T3 is simply V3 times T2 over V2, and this is now the beauty of it because we have T2, we just grabbed that from the table, and we have the ratio between V3 and V2, right? Let's check it out. We have the ratio between V2 and V3 right here. Right? It's a cutoff ratio. Okay, so I know V3 over V2 is 2. So V3 over V2 is 2. So we can simply do, this guy here is going to be our T2 that we just found. Let's just do this so we can see what, there you go. All right, so that's going to be our 862.3. And that's V3 over V2, so that's just times 2. Right, so that means that our T3 is just 2 times that. That's 1724.6 Kelvin. Brilliant, we got part A already. That's our T3. That's the temperature after the heat addition process. Done. Awesome. Next part. What's the thermal efficiency? Okay, so for us to find the thermal efficiency of this guy, let's do part B now. If we want the thermal efficiency, we know that's going to be the work over how much energy we had to start with, right? If we can use all the energy that went in as work, that's 100%. So we can either find the work or we can just find the two Q's, right? It's the same thing because we know work is, for this cycle, the same thing as the difference between Q in and Q out. So we can go ahead and do this. So that means that if we find the two Q's, we also can calculate the thermal efficiency. Right, so at the moment we don't have either of those, but we have defined T3. And with this T3 here, once again we can go to our table. So we can go to table A17 once more, and we can grab heaps of information for the third state. In this case here, what I'm going to do is I'm going to grab the information for VR, because I can use that to calculate my fourth state. And I'm also going to use enthalpy, because I know there's a constant pressure process from 2 to 3, so I can use the enthalpy to calculate the Q in. Right? Enthalpy for this state is 1910.6. And my VR3, its relative volume is 4.546. Okay, so now what I'm going to do is I'm going to use this enthalpy that I just found. I'm going to relate that to the enthalpy that I had before. Where is my enthalpy before? There you go. This enthalpy here for U2, for state 2. And I'm going to say that my Q in is just the difference between those two, right? So let's do that. So my Q in, let's do it this way, because from 2 to 3, delta P is 0, and no work other than, let's say no work other than boundary work, different than boundary work. That was supposed to be a W. right? So because of that, then my delta H equals my Qn. Right? That's the first law of thermodynamics, because let's actually do the whole thing. My delta U equals my work plus my Q, and then what's going to happen is this guy is going to be my P delta PV. My P comes out of the delta because pressure is constant, and I can send it to this side over here, and then we're going to have a term which is exactly the enthalpy, which equals delta U minus P delta V equals Q, right? And we know that this guy here is delta enthalpy, right? So therefore, delta enthalpy equals my Qn. So Qn equals H3 minus H2. Qn equals, what did I get? 1019.7 kilojoules per kilogram. Okay, so that's 1900 minus the 890. Now the other thing we need is the Qout, right? So for us to be able to find this guy here, the efficiency. So Qout, let's go hunt Qout now. So Qout is the one that happens from 4 to 1. And from 4 to 1, delta V is 0, which means that my work is 0, which means my delta U equals my Q, right? First law of thermodynamics. So as long as I can find U4, because I already have U1, I can find my Q. So just like before, let's go ahead and do that. I have that V4 over V3 equals VR4 over VR3. Because it's an isentropic process, right? We can only do that when it's an isentropic process, don't forget that. And therefore my VR4 equals my VR3 times V4 over V3. Cool. Now, V4 over V3. We don't have that per se, at least not straight off, but we can calculate that, right? Check it out. So let's just do, for now, let's just do V4 over V3. You guys remember that we have the ratio, the compression ratio of 16, which is V1 over V2. And the other thing that we know is that 1 and 4 are the same, right? So this could be 4 over 2 if you wanted to. So I can sub in over there, I can do that substitution. That's going to be 16 V2 over V3, right? These guys are equivalent. And then because these guys are equivalent, and we know the ratio between 2 and 3, remember, cutoff ratio, let's actually check it out. Make sure we remember what we're talking about. There you go. Cutoff ratio is V3 over V2, which equals 2, right? So if I have V2 over V3, that's 1/2, 1 over 2. Right, there you go. So that's equals 16 over 2, which is 8. Right, so I can go ahead and plug in where I have V4 over V3. That is right here. I can plug in 8. So that's just going to be my VR3, which we grabbed from the table just before, and is 4.546. So 4.546 times 8, which equals my VR4. So VR4 equals 36.37. Brilliant. And don't forget that with this, that's all we need to define the state, right? That's the whole idea behind having properties that are only dependent on temperature, right? So I can, once more, I can go to my table A17, and I can grab other properties. What do we want from this state? We only want internal energy, right? At least for now. I'm going to go ahead and grab temperature just because if you're doing this on the calculator, just 2 extra strikes, right? So interpolating it for temperature, so T4, oops, it's horrible. Let's do. So interpolating this for temperature, I got T4 to be 880 approximately. That's Kelvin. And I got my U4, my internal energy 4, to be 659.7 kilojoules per kilograms. Okay, so now that we have both internal energies, right, we have this guy and we have the previous one that we got right in the beginning when we went the first time to table A17, which is 214. We can use that difference to calculate our Qout. Where's my Qouts? Here it is. Okay, so that means that my U1 minus my U4, or vice versa if you want to just grab the positive number, as long as you know what you're doing, it equals my Qout. And in this case here we're going to have, I just do it, just keep going to the side. We're going to have 214.07 minus the 659 we just grabbed, 0.7. Okay, so I got that Qout is, well, it's going to be a negative because I did final minus initial. Negative 445.63. So 445.63 kilojoules per kilograms. Okay, so this is out. Again, negative is just telling you that it's out. If you're saying that it's out, you don't have to use a negative if you don't want to. So now with this information, with the 445, we can go back to finding out our efficiency, right? So I reckon I should just do it here since we have the number here. My efficiency will be difference in Q and Q out, so I can do 1 minus Q out over Q in. And that's going to be 1 minus Q out is the 445.63 we just found. And my Q in the same unit, don't forget that, the exact same unit is 1019.7. Okay, so that means that my efficiency is approximately 56.21%. Okay, so that's part B, 56.21%. So about 60%, 55%, I'd say, of the energy that goes in is actually used as work, right? The other 45% is discarded, or we lose it in the form of heat being rejected. Okay, last but not least, what's the mean effective pressure? Well, that's probably the easiest one to do, right? Because if you guys recall, the idea is that work is the integral of PdV, and we're going to use, instead of P, we're going to have a mean effective pressure. So the idea is that our mean effective pressure will be work divided by our delta V. Okay, so we don't have work per se at the moment, but we do have the two Q's, so we can use just the difference between them to calculate work. Okay, that is just the difference from 1,000 minus 445, that's going to be our work. Okay, and the delta V, we don't have it yet, but we can calculate because we have the first state pretty much defined, right? We have pressure, volume, and all of that. So let's go ahead and grab our delta V so you can plug it in. So this guy here is going to be 1019.7 minus 445.63. And that's going to be over a delta V that we don't know yet, but we can find out. So let's go ahead and find this guy here, delta V. Well, let's find our V1 first. Let me actually go ahead and change colors. Let's do blue. Okay, so I know my P1 V1 equals mRT1. This is air, so my V1 over mass, if I use R for mass, is going to be RT1 over P1. Okay, so R, you guys could have memorized already, but you can go on table A2 and grab it if you forgot what R is for air. That's 0.287. Our temperature for the first state is 300 Kelvin, and our pressure on the initial one is 95 kilopascals. Yeah, 95 kilopascals. Okay, so with that we can grab V1 over m, which is the same thing as the specific volume, right? Kilograms per, meters cubed per kilogram. And I have this as 0.906. Okay, now you can calculate V2 if you want to, or you can just use the relationship between the maximum and the minimum, because we know that. So it's really up to you what to do. So you can do the same equation. Okay, you can do the same equation here. Calculate your P2 first and then do this. Or, right, since we know the relationship between, we know that V1 over V2 is 16. That's one of the first information we have, which is the compression ratio. Then we know that my V2 equals V1 over 16, which means it's just going to be, we actually don't need to calculate this, right? We can just keep it like that. Because what we're looking for is the difference between V1 and V2, right? So if we go ahead and do delta V, we can sub in V2 for V1, so it's going to be V1, delta V equals V1 minus V1 over 16. It's a horrible 6 over 16. Yeah. So that's 0.849 meters cubed per kilogram. Oops. Okay, so now we have the difference, the delta V. This was all to find our delta V. So we can use this information back where we were. Yeah, we can plug that guy in there. So this is going to be divided by 0.849. And this is kilojoules per kilograms. This is meters cubed per kilogram. So go back here in the red. So my kilograms go away. Kilojoules over kilogram, that's the same thing as this guy, right? It's the same thing as kilopascals times meters cubed. So meters cubed go away, and we're left with kilopascals, right? So our mean effective pressure, let's go ahead and go this way. Mean effective pressure is, I got 675.87. Let's just round it up. 675.9. Okay, and that's in kilopascals. Do this neat. All right, so that's our part C of the diesel problem.